Hi everyone, welcome back to the series on applied electromagnetic theory. Today we are going to discuss lecture 23, which is cylindrical wave functions. So in the last couple of lectures, we looked at rectangular waveguides and we saw how to solve arbitrary waveguide problems numerically. And then we also looked at finite element methods. Now I think it's a good time to kind of move on from rectangular wave functions to another class of wave functions which are suitable for cylindrical geometries. The geometries which have cylindrical symmetries in some sense. Okay, so like I said earlier when we were doing the arbitrary waveguide stuff, that there are only few waveguide problems or electromagnetic problems that can be solved analytically, and that is when they coincide with some kind of coordinate system. And today we look at the cylindrical case. And this eventually will lead to cylindrical waveguides at the end of today's lecture. So there are metallic cylindrical waveguides and also fiber optics. Right? So fiber optic cables are also cylindrically symmetric, and we'll also look at that in the next lecture. So we need to kind of build up the basis of how to solve the wave equation in a cylindrical coordinate system. Okay, so that's the idea. So that's where we'll start from. The reason cylindrical waveguides are popular is that for the simple reason that they're much easier to manufacture. Right? Because you have cylindrical symmetry. So using a milling machine or a drill press even, you can easily manufacture cylindrical cavities or cylindrical waveguides. The same goes for fiber optics, right? So it is actually quite valuable to study them rigorously. Okay, so what we want to do is we want to solve the wave equation in 3D in cylindrical coordinate systems. Okay, so we'll start with the three-dimensional wave equation rather than the aperture wave equation, which was the 2D version of the transverse wave equation, because it doesn't really matter. We will see that the transverse condition kind of naturally comes out from this. This is the wave equation for a time harmonic potential. So it essentially is the Helmholtz equation, right? So in cylindrical coordinates, we know that del square becomes 1 over rho, dd rho d phi over d rho plus 1 over rho square d square phi, not phi, sorry, psi d phi square plus d square psi over dz square plus k square psi equal to 0. Okay, so we use separation of variables again because we have a coordinate system that the variables align with. And z of z. Okay, and then you substitute this and divide by psi, same as what we did earlier. And if you do that, you will end up with 1 over rho r d over d rho dr d rho plus 1 over rho square 1 over capital phi d square capital phi d phi square plus 1 over z dz square or d square z over dz square plus k square equal to 0. Again, this is not very hard to see. If you substitute phi equal to r phi z, then in this term phi z comes out. Then you end up with dr over d phi, dr over d rho. And since you're also dividing by psi, phi z cancels in the numerator and denominator, and you're left with 1 over r. And that's the 1 over r there. And the same thing happens for these two terms. Okay, so now in this equation, this is the only, this is only term that has z dependence, right? So these terms are constant with respect to z, which means that if you change z, this must also be constant with respect to z. So if you change z, since these don't change, this should also not change, right? So this should also be a constant. And we've seen that argument before. So which means z of z is, or rather I should say, which means 1 over z, d square z of z over dz square. I'll write that constant as minus kz square. You can also write this as minus beta square, doesn't matter. They are the same thing. Okay, so of course the solution to this is either a linear combination of sine and cosine or a linear combination of complex exponentials. They are both okay. You can just simply substitute this into this differential equation, and you'll see that this pulls out a minus kz square. So you essentially end up with satisfying that equation. Okay, b e to the minus I kzz. Okay, so now that you have this, the equation on top becomes rho over r, d over d rho, rho dr over d rho, plus 1 over capital phi, d square capital phi over d phi square, plus k rho square equal to 0. So what I've done is I made the substitution k rho square for k square minus kz square, and I multiplied on both sides with rho square. Okay, so this term now is k rho square, and then I multiplied on both sides, so this becomes rho, this goes away, and then you get this times rho square equal to 0. That's exactly what we have here. Okay, so once again, in this equation, it's the same argument that only this is a function of phi. It's not a function of phi, this is not a function of phi. So if phi is changing, then since these two don't change, this also should not change. Okay, so this should also be a constant. And of course, this cannot be a function of rho because we know phi is not a function of rho. Right? So it's not a function of rho, it's not a function of phi, which means it's a constant. Right? So we also get that capital phi of phi is some linear combination of complex exponentials. Let's say I nu phi plus d e to the minus I nu phi, where I'm writing this as minus nu square. Okay. Okay, so substituting that in as well, what happens to the wave equation? It becomes rho d over d rho times rho dr over d rho plus a rho square minus nu square r equal to 0. So I've gone on and multiplied on both sides by r. So you get this becomes this term multiplied with r, and here this guy goes away. So you're left with this term. Right? And of course, you don't need to write partial derivatives because we know that this is only a function of rho, not a function of phi and z. Okay, so it's the total derivative. Okay, so we'll make a change of notation. We'll replace r with r nu because we know that r is a function of nu, because in this equation you have this new term. And apply product rule. Okay, so we're kind of separating this. It's a derivative of two functions, product of two functions. And we also want to multiply and divide by k rho square. Okay, k sub rho square. Okay, so if you do that, then you end up with k rho square d square r nu over d of k rho square plus k rho dr nu over d k rho plus k rho square minus nu square equal to 0. And this is fairly easy to see. So when you take the product rule, you get rho square times d square r over d rho square, and that's what this is. And I'm multiplying and dividing by k rho square. So you get 1 k rho square here, 1 k rho square there. And the other term is dr over d rho times d rho over dr. Sorry, d rho over d rho, which is 1. So you end up with just dr over d rho. And then now I'm multiplying and dividing just by k rho. So that comes out there. And then this term is the same as this term. There should be an r here. Oops, it's too much. So r nu equal to 0. Okay, and then we'll make another change of variables, rho tilde, which is k rho rho. Then you end up with this differential equation, d square r nu over d rho tilde square plus 1 over rho tilde dr nu over d rho tilde plus 1 minus nu over rho square r nu equal to 0. Okay, so this equation is called the Bessel differential equation. Try that again. So this is the Bessel differential equation. And solutions to these equations are called Bessel functions. Okay. So solutions are there are multiple classes. So we'll see them. So let me write this out first. So solutions are of the form, it's a linear combination of two functions, j nu, j sub nu, plus b sub n sub nu, b times n sub nu, k rho rho. Okay, this function is called the Bessel function of the first kind and order nu. And this one is Bessel function of second kind and order nu. Okay, so these Bessel functions are special functions, similar to sine and cosine. But sine and cosine are also special functions in some sense, which means that they cannot really be written as some kind of a polynomial, right? They need to be written as an infinite series and not a finite polynomial expansion. They don't have any finite polynomial expansions, right? So essentially, these functions are known to satisfy this differential equation. Okay, so they are special functions, and we'll try to understand them and get some intuition for them. Of course, you're very familiar with maybe sine and cosine because you've seen them many times, but Bessel functions will also become hopefully equally familiar as you keep using them over and over, right? So it's just a matter of using them often. Okay, there's another class. So we'll try and understand the intuition behind these different classes and so on. But another set of solutions are called Hankel functions. These also satisfy that equation. H nu 1 plus b h nu 2 of k rho rho. Okay, so these are called cylindrical Hankel functions, because there's also a spherical Hankel function, which we'll see later. Cylindrical Hankel functions of the first and second kind and order nu. Okay. So there is a very close analogous kind of relationship between these Bessel function, Hankel functions, and sinusoids and exponential functions. So this function is something like a cosine. This one is something like a sine. This one is something like e to the ikr. And this one is something like e to the minus ikr. Okay. So essentially, this is like standing waves. Right? So we know that standing waves are typically represented as sine and cosine because it's essentially a forward propagating wave e to the ikr, backward propagating wave e to the minus ikr. And obviously, when you add them, you end up with cosine, right? Or you subtract them, you end up with sine. So in fact, we know that standing waves are a combination of two propagating waves in two different directions. That's what you get when you have a reflecting boundary. And indeed, in this case as well, in cylindrical coordinates, these guys represent standing waves, and we'll see what they look like. So what do these represent? The cylindrical Hankel functions represent propagating waves. It's similar to e to the ikr and e to the minus ikr. So that's what the cylindrical Hankel functions are. Okay. Okay, so what do they actually look like? Let's plot them out. That's the, or rather I should let me try that again. So let's say this is x, this is jnx. So I'm assuming jn here, n subscript n is an integer subscript. So the order is integer, and we'll see when that shows up. Basically, your Hankel function looks something like this. That's for n equal to 0. And then n equal to 1. Should draw that a little bit more carefully. So this is n equal to 1. And then you have, let's say, n equal to 2, does something like this, and so on. Okay. So let me move this to the left a little bit. And then we can also draw the second kind, Bessel function of the second kind. This is n subscript n of x. And these guys look something like this. So this is n equal to 0. And you have equal to 1, and so on. Okay. So already from this, you can get quite a lot of intuition for what these look like. So you can see basically that as x increases, this looks a lot like a sine or cosine. We'll see what exactly the expression is for large values of x. Now for small values of x, of course, they don't look at all like sine and cosine. This maybe looks like a cosine, the first one, but the others don't look like cosine. They look more like sine, right? Because they go to 0 at x equal to 0. Now for the second Bessel function of the second kind, Bessel function of the second kind, there is a singularity when x equal to 0. Right? When x equal to 0, these two go to infinity. Okay? So that has implications, right? Because if I have a waveguide that has x equal to 0, let's say this is the origin, and I include the origin within my solution domain, which means I have to have a field here that is finite. If the field has to be finite, it cannot be expanded in terms of the Hankel function, in terms of the Bessel function of the second kind, right? Whereas it could be expanded in terms of these guys. So we'll see that that actually plays a role when we do the cylindrical waveguide. But if I have a coax cable, then for a coax, I don't need to have any field here. Right? The field solution only exists in this region. So I've excluded the origin from my domain of interest. And in that case, I can expand both in terms of Bessel functions of the first and second kind. Okay, so this already has some implications, which is kind of interesting. Okay. Now, if phi is entire domain, right, which means that all angles of phi are included within the solution space, implies nu becomes an integer, becomes an integer. Okay, so why is that? So if you look at capital phi of phi, it's a e to the I data phi or nu phi plus b e to the minus I nu phi, right? Okay, which means that if phi is entire domain, right, which means it's periodic, so phi plus 2 pi is equal or equivalent to phi, right? So if I put phi plus 2 pi in here, then this becomes e to the I 2 pi nu times e to the I 2 pi phi. But this must be equal to e to the I 2 pi phi, right? Which means this term must be 2 pi n for periodicity, right? Essentially, it just means that nu must be an integer, okay? Implies nu equal to n, some integer. This belongs to integers. Okay, that's nice, and that's the reason we basically only care. I mean, in some problems you don't get this. So essentially, if I have an angular sector waveguide, right? So I have a waveguide that's an angular sector like that, and that is propagating, something like a pizza slice, right? Then you don't have phi everywhere, and in that case, actually, you do get um, rational, not necessarily integer values um, for nu. Okay, but at least in fiber optics and cylindrical waveguides, this is the case. So we'll start by maybe just treating this case. It belongs to integers. Okay, and I should also mention that there are relationships between the Hankel functions and the Bessel functions. And very similar to sine and cosine, they are related by the I, right? H mu 2 is k rho rho equal to j mu k rho rho minus I n nu k rho rho. So this is like cosine, this is like sine, cosine, sine, e to the ik, e to the minus ik, right? And so very similar to those. So this basically represents outward propagating waves. So if I have some cylindrical geometry, waves that are going cylindrically outward are represented by this, similar to how you have e to the ikr is representing outgoing waves. And this represents incoming waves into the cylinder. Okay. So there are many, many useful and important properties of Bessel functions. There are entire books written on just Bessel functions. So we won't go through all of them, but we'll kind of look at several properties just to kind of build up our intuition for them. So the first one is asymptotic forms. So I'm not going to derive any of these relations. I'm just going to assume that somebody else has derived them, which is actually the case, and we'll just look at the final equations. Okay, so limit k rho rho tends to infinity. So what happens when the argument of the Bessel function goes to infinity? It approximates 2 over pi k rho rho cosine k rho rho minus 2n plus 1 over 4 pi. So you can kind of see explicitly it looks like some kind of a phase shifted version of the cosine. This basically looks like cosine, but it's slightly damped. Right? It's damped by this 1 over square root of rho factor. So as rho goes to infinity, this slowly oscillates down to 0, right? Because you have this 1 over square root of rho factor. Okay. Then you have limit k rho rho goes to infinity, n sub n k rho rho is approximately equal to 2 over pi k rho sine k rho minus 2n plus 1 over 4 pi. Limit k rho tends to infinity. So I mean, hopefully this makes sense that this is k subscript rho times rho goes to infinity. Hankel functions, of course, as you can guess, would be related to exponentials. Right? And you can directly see that from the previous relationship, the Hankel function in terms of the Bessel functions. K rho minus 2n plus 1 over 4 pi. And I'll just put, say, comma 2, means this becomes minus. Okay. So those are the asymptotic forms. And from that, you can explicitly see that they look like cosine, sine, and complex exponentials. But it's interesting that even when you're at low, smaller values of k rho, these equations still hold. Right? This is still true. Okay. Now I want to discuss another slightly different class of solutions, which arise when you have, so we know that k rho is square root of k square minus az square, right? And when kz, mod kz rather, is greater than k rho becomes imaginary. And we saw that when you have k becoming imaginary, this is essentially an evanescent wave. So how do you actually represent evanescent waves in cylindrical coordinates, right? So we want to see that next. Okay, so I'll assume k rho is equal to some I alpha, where alpha is real. Then if I go back to the wave equation, it was rho d rho. At one point, it was this value. It looked like this, plus k rho square minus nu square r equal to 0. Now I'll substitute k rho as I alpha, implies I have rho. Maybe I can just do it here. So if I substitute I alpha, what happens? I get a minus out here, an alpha out here, and a plus out here, right? Okay, and then again, I'll do the multiply and divide by alpha square and replace alpha rho with rho tilde and r with r nu. Then you end up with a differential equation that looks like this: d square r nu d rho tilde square plus 1 over rho tilde dr nu over d rho tilde minus 1 plus nu over rho tilde square r nu equal to 0. Okay, so this equation slightly different than the Bessel equation. It's not good. Okay, so this is called the modified Bessel equation. And solutions to this are called the modified Bessel functions. In alpha rho and kn alpha rho. Okay, so these are the modified Bessel functions of the first and second kind and order n. Okay, so what do they look like? So let's plot them. X, n of x. Maybe I can Make it a little bit smaller. It's equal to 1. So this is when n equal to 0. And all the other values have n start at 0. 1, n equal to 2, n equal to 3, and so on. Okay, maybe I'll erase the last one. And similarly, you also have kn of x. Maybe I should put x up here. No. Here. And these look like decaying exponentials. And they all asymptotically decay. So n equal to 2, n equal to 0, n equal to 1. So for consistency, maybe I can make the same color scheme. Equal to 2, equal to 1. Okay, so we also want to look at some of the properties of these functions. So one thing is you can show that they're directly related to the Bessel function as follows. In alpha rho. So in alpha rho is related to the Bessel function of the first kind, and an alpha rho is related to the Hankel function of the first kind. This one, an alpha rho. They also have asymptotic forms. So limit alpha rho tends to infinity, and you can guess that this looks like a real exponential. Approximately e to the alpha rho divided by square root of 2 pi alpha rho. Limit alpha rho tends to infinity. An alpha rho is approximately equal to square root of pi over 2 alpha rho e to the minus alpha rho. So those are the asymptotic forms. Okay, so these represent evanescent waves. Okay, so I should write that here. So these are evanescent waves. Okay, so of course, this represents the evanescent kind, and this is the growing exponential. You don't really see this very often, but it can show up sometimes. For example, in negative index lens, right? But this is the real exponential, the real evanescent, right? Which means it's decaying. Okay. So now we want to look at some useful properties of these Bessel functions, which make them actually unique compared to trigonometric functions, which don't usually have these kind of properties. So these properties actually have many nice implications, which we will see later, but we want to first list out what these properties are. Okay, so the first is what is called recurrence relations. Okay, so r nu minus 1 plus r nu plus 1 is equal to 2 nu over rho r nu, where r nu can be j nu, n nu, h nu 1, or h nu 2. So for all of these values, all of these Bessel function and Hankel functions, you have this nice recursion relation, right? So if you know R0 and you know R1, you can find R2. And then from R1, R2, you can find R3 and so on. So you can find all the Bessel and Hankel functions if you know two of them, which is very nice. It's a very kind of elegant relationship. Something like this also exists for the modified Bessel functions. nu plus 1 equal to 2 nu over rho I nu, and k nu minus 1 minus k nu plus 1 equal to minus 2 nu over rho k nu. Okay. Then there are also very nice derivative properties. So if I take dr d rho, so derivative with respect to rho is nothing but r nu minus 1 minus r nu plus 1. Okay, similarly d over d rho, rho to the nu r nu rho is equal to rho to the nu r nu minus 1. And here r nu is Bessel and Hankel functions. D rho, rho nu, r nu rho is equal to minus rho to the minus nu r nu plus 1. Okay, so modified Bessel functions also have similar relations. 1 over 2 I nu minus 1 plus I nu plus 1 d k nu over d rho equal to minus 1 half k nu minus 1 plus k nu plus 1. Okay. And lastly, d over d rho, rho nu, I nu rho is equal to rho nu, I nu minus 1 rho. Okay, and the same thing, I can replace this with k nu minus 1. This becomes rho minus nu, rho to the minus nu. I should say minus rho to the nu. And this becomes k nu rho. Okay, that's the last relationship. Okay. So beyond the derivatives, there are also other properties. So one interesting property is called the Wronskian relation. Which is, it's actually quite useful. J nu rho n nu prime rho minus j nu prime rho n nu rho is equal to 2 over pi rho, where the primes represent derivative with respect to rho. Okay, so this is derivative. Then you also have j nu rho, h nu 1 prime rho minus j nu prime rho h nu 1 rho is equal to I times 2 over pi rho. Okay. Okay. Then the last set of relationships is the orthogonality relationship. Orthogonality relations. So similar to how we saw for sine and cosine, sine and cosine are orthogonal to each other and also orthogonal to themselves, right? So cosine m pi over x, m pi over a x times cosine n pi over a y integral over the aperture of a rectangular waveguide, we saw that was 0. Right, so similarly here you have integral 0 to a, where a is the radius of, let's say, the waveguide. Doesn't have to be waveguide, it can be any radius actually, that this is true. X nu p over a rho, j nu x nu q over a rho, rho d rho equal to 0. Okay, we'll see what x nu p and x nu q are. But you also have another relation, which is j nu x nu p prime over a rho times j nu x nu q prime over a rho d rho equal to 0. Okay, x nu p and x nu q are zeros of the Bessel function j nu x. Here we are also assuming p is not equal to q. Okay, that's when you have orthogonality, of course. X prime nu p, x prime nu q are zeros of the derivative of the Bessel function. And again, p is not equal to q. Okay, when p is equal to q, you have a slightly different relation. So this reduces to j nu square, x nu p over ax, rho d rho. And this becomes a square over 2 j nu plus 1 x nu p square. And you also have for the j nu prime j nu square x nu p prime over a rho d rho is equal to a square over 2 1 minus nu square over x nu p prime square times j nu x nu p prime square. Okay, so this is obviously 0 of the derivative of the Bessel function. This term is not 0. Okay, and similarly, this is the derivative of this is the 0 of the Bessel function of order nu, whereas this is nu plus 1. So this is also not 0. Okay, so this is in some sense the normalization factor that should be used if you want to normalize these modes, right? Because when you have a normal mode that's normalized, its inner product with itself should be equal to 1. So if you basically divide by the square root of this, then you will have that normalization. And that's typically not done, but so it's important to know these values. Okay, so that basically covers all of the properties that we care about, at least most of the properties that we care about with Bessel functions. So we saw that there are 3 different types. So there's the Bessel functions of the first and second kind, which represent standing waves. There's the Hankel functions which represent outgoing and incoming waves. And also there are modified Bessel functions which represent the evanescent waves. Right, so now I think we have enough of a framework to start discussing the waveguides. So let's do that next. Okay, so the first thing we'll do is we'll discuss cylindrical waveguides of metallic boundaries, basically a metallic pipe. Okay, so cylindrical waveguide. So I'll make a coordinate system, X, Y, and Z. My waveguide geometry is kind of something like this. And then it kind of goes out like that. And at some point on this waveguide is represented by rho, P, and Z. Okay. This surface is called S. It's metallic. So once again, solutions of the TETM kind. So the TM solution correspond to is equal to 0 at the boundary. This is Tm. And the boundary condition for Te is that the derivative with respect to rho, because the normal component is rho, is equal to 0. This gives the Te modes. Okay. So now recall that pi, which was the Hertz vector potential, was psi x comma y e to the plus or minus I beta z. So this I can write as psi now in cylindrical coordinates as rho comma phi e to the plus or minus I beta z. So when we derived from the 3D wave equation, we saw that it pulled out an e to the I azz factor. That's what this is. And the rest of it we're writing as rho times phi. And this is the, again, same kind of decomposition. So this is the aperture distribution of the potential, and that potential is propagating at e to the I beta z as a wave in the z direction. Okay, so once again, separation of variables, which we just saw. This can be written as some coefficient Jn, k rho rho, plus another coefficient Nn, k rho rho, times either sine n phi or cosine n phi. Okay, but so there are a few things. So first thing is that sine and cosine are degenerate, because in this problem you have phi symmetry, right? So if I have a sine solution, if I just rotate phi by 90 degrees, or if I rotate the waveguide by 90 degrees, it gives me the cosine solution. So solving for one of them is enough. Okay, I don't need to solve for both. So we'll just pick cosine as arbitrary, as what we're solving for. Another thing is that this term must go to 0. Right? Because in our problem, we have 0, or the origin is part of the solution domain, so we can't have fields blowing up to infinity here. And since this has a singularity at the origin, b is equal to 0. So this essentially gives us that the solution of the form an, jn, k rho rho, cosine n phi. Okay, so now we want to apply the boundary condition. So the Tm boundary condition implies that this whole thing goes to 0 when rho equal to a, where a is the radius, let's say. So I haven't written that down. Here you screen. So this is our a. Right, so under that boundary condition, this must go to 0 for all values of phi. Right, so the only way that's possible is if this term must be 0, because you want this to be 0 for all values of phi. So applying the boundary condition implies that Jn k rho a is equal to 0, right? So that means k rho a is nothing but the zeros of the Bessel function, which are k and p. Which are x and p, which we defined earlier. Right? Implies that k rho, which is the unknown propagation or the radial propagation constant, the radial wave number, is nothing but k and x and p over a. And this is very similar to what we did in rectangular waveguides, right? So in rectangular waveguides, we saw that kc was n pi over a square plus n pi over b square. So let's assume we're looking at just a mode that doesn't have n. So then kc would just be n pi over a. And n pi is a 0 of cosine. Cosine n pi is 0, right? So you have a 0 of the basis function divided by a. Similarly here, you have a 0 of the basis function, which is now Bessel, divided by a. So it's not very different. Right? So once I know k rho, now I can write beta. Right? So now my beta is, or kz, which is the wave number in the z direction, is k squared minus x and p over a squared. Okay, so from this, you can get the cutoff frequency. You set this to 0, and that will tell you that k is equal to xn over a. So k cutoff, kc, should say k cutoff, is nothing but xn p over a. Implies the cutoff frequency is, for np, for Tm modes, is nothing but xnp over 2 pi a square root of mu epsilon. Okay, you can do the same thing for TE modes by applying the Neumann boundary condition. And since there's a derivative involved, you would get Jn prime of k rho A equal to 0 implies k rho for TE modes is xn prime over A, where xn prime is the 0 of the derivative of the Bessel function, right? And similarly, you can show the cutoff frequency for TE modes for NP is xnp prime over 2 pi A square root of mu epsilon. Okay? So of course, you can also get the fields. I won't write all of them. Maybe I'll just write a couple of them. For TM modes, E rho component is some E naught constant, I beta, xnp over A, Jn prime, xnp over A rho, cosine m phi, e to the I beta z. Again, similarly, you have E phi, Ez, H rho, and HP. And you can find them in the textbook if you like, but you get these fields. And what we want to see is what do these fields actually look like? What is the dominant mode, right? So try it out. So that's one. Maybe I'll just make a copy. It's one copy. And we have another copy. So let me move these a little bit. Okay. So the dominant mode in the waveguide is TE11 mode. So this is the mode with the smallest eigenvalue, right? Kc square should be the lowest because it is the minimum of the variational problem, which we looked at in the last lecture, right? Okay. What does the mode actually look like? So the electric field distribution looks something like this. And then it kind of goes to 0 here and 0 here. Okay. So this kind of makes sense because, the n index is equal to 1, p index equal to 1. Now, when the n index is equal to 1, you will have cosine distribution, right? You have a maximum, goes to 0, goes back to maximum, and then goes back to 0 and goes back to maximum. And that's what cosine phi is, right? Now, when the p index is equal to 1, you have the derivative of the Bessel function, right? So you basically have J1 prime, right? So J1 had a 0 at rho equal to 0, at x equal to 0, and then it kind of did something like that. But the derivative is not 0. So the derivative actually is something like this. And then you can also see that from the recurrence relations or the derivative relations, right? So in fact, Jn prime when p equal to 1 is, or when n equal to 1 is has a maximum in the middle and then decays, right, along rho. So that's why the mode looks like that. The second mode is the TM01 mode. So that's the next mode that starts to propagate, and that's radially symmetric. And that also you can see because n is 0, you have cosine, they have no distribution along phi, and this whole term goes to 1. So you only have an expression in terms of Jn prime, right? So, and you have to have a null in the middle because these are all electric fields pointing out, right? And then the next higher order mode is, something like that. That's the TE01 mode. And then the next higher order mode after that is TM11 mode. So TE01 is something like this, propagates like that. This is actually degenerate with the TM11 mode, which means they both have the same KC. Okay, so let me actually draw this out. So it's basically electric field is going around in circles. And of course, this also must have a null at the center, right? So there should be a null here and also a null at the edge because you have electric field is in field direction. So to satisfy the boundary condition, it must go to 0. So your modal distribution as a function of rho is a null in the middle, null at the end, maximum. Here there's only a null in the middle and then it goes to a maximum at the edge. Okay. Now an interesting mode that's related to these is the next mode, which I'll draw a little bit smaller, is the TM11 mode. So the TM11 mode looks something like this. There's a null here, a null here, and there is field distribution, kind of goes out like that. And then again comes in, and then again goes out like that. Okay, so I'll just draw the arrows to be this way, and then the arrows flip, and then again the arrows flip. So this is a higher order mode. Okay. Okay, so why is this mode important? Now, if I take this mode and add it with this mode, so let's say, I put this on the other side, TM11. Now, if I take these two modes and I add them, assuming I have the right amplitudes and phases or whatever, so you add them, that results in what? That results in a node which looks like this, right? So over here, this is pointing this way, this is pointing this way, so they cancel out. Even here, this is pointing up and this is pointing down, so they cancel out. Right? So you end up with a mode that actually looks something just like this. You only have field distribution in the middle. You don't have any field distribution anywhere else, right? Because of course here, both the modes are 0, and here they cancel out. So you have a nice kind of this field distribution that is only concentrated in the middle. Then it decays out to the edges. Because it decays out to the edges, the aperture profile, amplitude of the aperture looks something like a Gaussian. You have maximum here, and then it decays out. This looks something like a nice Gaussian, right, along rho. Which means that the far field distribution, which we know is the Fourier transform of the aperture field, is also going to be Gaussian. Which means the far field distribution does not have any side lobes, right? That is exactly what a Potterhorn does. So we looked at Potterhorn once when we did the long video on 6-hour long video on antenna design. We also used it a couple of times on this channel. And I like it because it's a very elegant design. So maybe I'll spend a couple more minutes on explaining how that works, which we've already done in the past. Maybe I'll skip it. So you can go back, since now you know what these modes look like, you can go to that video, the 6-hour long antenna design video. It's called, I think, Designing Every Antenna in HFS or something like that. Open the description. There's a list of antennas. You can click the section on Potterhorn. And then there I have a nice slideshow on showing you how actually the Potterhorn radiates without any side lobes. The downside, of course, is that it's kind of narrowband because you need to have two modes that add up and they only add up at one frequency. So, but still, it's very elegant design, very easy to manufacture and has no side lobes. Okay, so that's about cylindrical waveguides. We've done quite a bit. So it's a good place to stop. And in the next lecture, we look at fiber optic cables and some properties of cylindrical wave functions. Okay, so we look at the Green's function for a line source, which is kind of nice. Okay, If you have any questions, you can leave them in the comments. If not, I'll see you in the next one. Thank you.